Hello and welcome to this video. I'm Transistor Brains, and today I'm going to show you how to build this circuit. It's a simple decade counter circuit. This circuit's useful for a lot of things. It can be used to count to n, so if you need to count a specific number of clock pulses. If you need to make a frequency divider, it's great for that as well. This sort of circuit, not necessarily this exact circuit, but this sort of circuit is used in CPUs to help the instruction register and a bunch of other things. I specifically needed this circuit for a project I was working on. The project wound up getting redesigned to the point where I didn't need a counting circuit anymore. But I thought I'd share with you guys how I made this and how simple this construction really is. So the chip that we're going to use to accomplish this is the CD4017B. And so if we look through the spec sheet, there's a lot of good stuff in here. But what we really care about is on the first page. Right here, we have the pinouts. So from pins 10 through 7 and pins 11 through 9 are outputs, and pin 16 is our power, pin 8 is our ground, pin 14 is our clock input, pin 13 is our clock inhibit, so this is a way that we can turn the chip on and off. Pin 12 is our carry out, so if we want to ripple it down to more chips, that's how we do that. Pin 15 is our reset. This is essentially another way of inhibiting it. The only difference is no matter what the output is here, it will set it automatically back to 0. So right here, I've got a simple 555 timer set up in an astable output right now. So if I hook up my power here, got my ground right there, or my power right there, my ground right there, you'll notice their output right here is blinking. I've got this set up so I can go slower. You see it's a really slow blink there. But this speed will do us fine for this. So we're going to start with our little microchip right here. Every microchip will have some marking telling you which side is the front, which side is the back. So right here, I don't know if you can see it on camera, but there's a little divot right here. And then that would make this pin 1, which if we remember is an output, and this pin 16, which is our power. So initially the legs are a little splayed out, which makes it hard to put it in a breadboard, but if you press them against a flat surface and bend them just a little bit, it makes it a little bit easier to put in. I'm gonna stick that in there. Now, the first thing I want to do is want to connect my power and my ground. So pull out some cables here. So this pin right here, which is pin 8, we're going to connect to ground. Oh, and I'm going to disconnect my power and my ground output here so that we don't mess something up by accident. So connect power here. Next, we want to connect our clock. So we want to go from pin 3 on our 555 timer to pin 14 on our clock, on our decade counter. So it's 16, 15, 14. Gonna connect that in right there. So now we've got our power, our ground, and our clock. Next, we need to set our signals for clock inhibits, which is pin 13, and reset, which is pin 15. In this case, we want to tie them both low. So we'll tie this to ground and this to ground. Now, if we were to power this up right now, you won't see it, but if we were to power this up right now, it would just simply cycle between output 0 and output 9. But we want to see that, so let's add some LEDs in here. We're going to add in 10 LEDs because it's a 10-pin output, 0 through 9. So add them in like this. And then next we'll add in some resistors. Now these resistors are simply current limiting resistors. We don't care too much about their value, but we don't want super high value. If we keep them consistent values, we'll have the consistent brightness. So I realized as I was adding these resistors that I added 8 LEDs instead of 10 LEDs, so I took care of that. I've got 220 ohm resistors here as current limiting resistors. Really any resistance value will do. They're simply there to keep your LEDs from burning out. And you can get away with not using the resistors, but you run the risk of your LEDs burning out. So now we're going to wire up our LEDs. Now, the output, as you may have noticed from the pinout I was showing earlier, is not in a convenient order. That's output 5 there, that's 1, that's 0, that's 2, that's 6, so on and so forth. So it's a little unusual, but if you take your time and double check your work, you'll be fine. So I'm going to wire them from output 9 down to 0. I find it a little bit easier to work that way. You might find it a little bit easier to work the other way. Alright, I've got all my LEDs plugged in now. Now we're going to fire it up and show you what I'm talking about. So plug in our 5 volts here. And plug in our ground. You'll notice right away it starts counting from 0 to 10, from 0 to 9. We can decrease our speed here and get a slower count. And you'll notice it's every time the clock transitions on the rising edge, so it goes from a low signal to a high signal that it transitions onto the next one. Now we don't need it that slow, that was just an example. Another thing you might have noticed is it didn't necessarily start on 0. In fact, I think that time it started on 1, sometimes it'll start later. And that's what our reset pin is for. So what we're going to do here is we're going to take a little push button right here, and we're going to wire it up to our reset. So let's pull out our power here. Now we put in our push button. Now I want this push button to be default low, so grounded until it's pushed, then I want it to pull it high. So what I'm going to do is I'm going to take a resistor and I'm going to put it between this pin right here and ground. Then I'm going to take my reset signal, which is pin 15. Plug in a longer wire here, so we'll reach all the way. And plug it in there. So now by default, the pin will be grounded. But when I press it, what's going to happen is this connection here between 5 volts and the other end will be active. So when I press it, it'll be in the reset state. And what you'll notice is it'll stay with this LED lit, pin 0, or output 0, even though this clock will be flashing. And when I let go, it'll count. And no matter where it is in the count, if I press the reset, it'll go back to 0. So let's plug it in. So our 5 volts here, which for some reason does not like plugging in right the first time. And then our ground. It's not plugging in right. There we go. So if we press our reset, it's stuck on output 0 even though the clock is going. And if we let go, it'll continue. Press our reset, it goes back to 0. And it continues to count. Now some of you may be aware of something called button bouncing, where when you press a button down, the two plates contact, but they sort of bounce back and forth a little bit and create a little bit of a signal. If you're creating something where timing is very important, button debouncing, which is the act of getting rid of those bounces, is important. But for something like this, we don't care too much about button debouncing. If we were using this in some sort of timing circuit where we need to count a certain number of pulses, then that would be very critical. But for this, it doesn't matter. Now the other thing is maybe you don't want to count to 10, maybe you want to count to 20, or maybe you want to count to 15 or something else. How do you do that? Well, you can just add another chip, and then you connect the carryout on the first chip to the clock of the second chip, and then everything else is the same. And I'll demonstrate that now. Alright, so you can see that I've done that here. Made a few changes here. First of all, I added a second chip here, the 4017 decade counter. I moved my LEDs to the side. I got rid of the current limiting resistors. Now those are still a good idea to have, especially on a lower clock cycle where you will really notice your current draw. I got rid of the current limiting resistors to save space. I wouldn't recommend doing this, but I do want to demonstrate that you can run them without current limiting resistors and it'll still work. So from here, I'm going to connect my power. And you'll notice right away it starts counting. We're going to hit reset, and it'll start counting from the beginning. So every time this cycles through once, this side goes to the next counts. So from here we can count to 100 because we count 10 here and then 10 here, so 100 counts. This is especially useful if you're looking to count a specific number of cycles, or if you want to divide a frequency. You'll notice that these stay on for a lot longer. If I don't nudge things, these stay on for a lot longer than the clock pulses do. So they're great for dividing frequency. So if you want to take a higher frequency and go to a lower frequency, that's a great thing for them. Another thing you can do, which we're not going to do in this video, but you can add an AND circuit here, an AND gates. So you would move the button down, you would add another microchip, and then you would take your reset, or not your resets, your clock enables, and you would tie them to the output of an AND gate, and then you can AND whatever values you want here, and it'll count to that value. So for example, if I want to count to the value of 15, I would take the output 5 here, and it with the output 2, or output 1, sorry, here, so the second output, which is right here, and those together, and then that would stop the clock. So it would count to that point and then stop, and then you'd hit reset and go again. You can build another circuit to reset it, so you're always counting to 17 or whatever you want. And that is it for this tutorial. Be sure to let me know what you guys think. I'm looking for feedback. What did I do good? What did I do bad? Anything you didn't understand? Anything I could have explained better? And be sure to like, comment, subscribe. And also let me know down in the comments what you're planning on using this sort of circuit for. I'm always on the lookout for cool projects. Love seeing what other people do.